Hello, welcome everybody. So we are in our fifth module, and as we saw in our introduction class, fifth module is about rotational motion, kinematics and kinetics of rotational motion, and about the vibration. So in the first part, that is kinematics and kinetics of rotational motion, we have seen the basic concept and the problems on kinematics of rotation. That is, we have completed this part. We have completed kinematics of rotation, and we have seen the equations of motion of rigid body rotating about a fixed axis. That was kinetics. That is, how to relate the angular displacement, angular velocity and angular acceleration with respect to time. We saw how to relate theta, angular displacement, omega, angular velocity, alpha, angular acceleration with respect to time in our first part. That is, in the first two videos. We saw the concept and some problems. Now, from this class, we are going to continue. We are going to study about kinetics, kinetics of rotational motion. So we all know what is the difference between kinematics and kinetics. So kinematics means we are relating the geometrical properties. So we use the equation of motion to find the relationship between the angular displacement. Since it is rotational motion, we will call the displacement as angular displacement. So we know angular displacement, angular velocity and angular acceleration with respect to time. Now, coming here, it is kinetics. So, kinetics we know relating the forces, relating the internal forces and the external forces. So, we start with Newton's second law, that is force is equal to mass into acceleration. So, this is how we define our kinetics, how we enter into our kinetics problems. Now, here kinetics of rotational motion. So, see, when it comes for linear motion, kinetics will be about a constant force. Kinetics occurs by the application of a constant force. Since here it is rotational motion, kinetics comes when we are applying a constant moment. So we apply a constant moment, also known as torque. So we apply a moment or torque. Then the problem becomes kinetics. So today we are going to see basics and two problems on the rotation under the constant moment, about the kinetics of rotational motion. So rotation under a constant moment, that is kinetics for pure rotation. See, why it is called a moment? For linear motion, it was a force. For linear motion, in order to see an object is moving, you need to apply a force in order to change its direction or in order to move it forward. Then the motion is rotational. If you want to move an object in a rotational manner, you need to apply a moment or a torque, that is force into distance. So when we are talking about, when we discuss about curvilinear motion or rotational motion, we have to apply the external force applied will be a moment. So moment or torque both means the same. So we represent this moment or torque as capital M or capital T, both means the same. So first of all, we will see what is a torque. So torque is a twist caused by a force acting at a defined distance from the axis. See, that is why we call it as rotation about a constant moment. Rotation with the help of a constant moment. Kinetics. Okay, so torque is a twist caused by the force acting at a defined distance from the axis. Now, Let us consider a rotor of a motor rotated about its axis due to the force tangential to the armature. So we are applying a torque. Now we know moment or torque is equal to, that is some force into distance. Listen, we know mass is equal to force into acceleration. Mass is equal to force into acceleration. Newton's second law. When it comes to linear motion, force is equal to mass into acceleration. When it comes to rotational motion, our force is replaced by moment or a torque. So force is replaced by moment or a torque. Mass is replaced by mass moment of inertia. Acceleration is replaced by angular acceleration. So for linear motion, force is equal to mass into acceleration. For rotational motion, torque or moment is equal to mass moment of inertia into angular acceleration of the body. So T, summation of torque or torque T or M is equal to mass moment of inertia is I, angular acceleration is alpha. See now this M naught represents moment with respect to the center, that is the center of rotation. Here again I naught is with respect to the center, that is why it is given as I naught. In general you can take M is equal to I alpha or T is equal to I alpha. So I repeat, see for kinetics is relating the forces. So for linear motion we know force is equal to mass into acceleration, Newton's second law. For rotational motion, force is replaced by moment. So moment is equal to mass is replaced by mass moment of inertia. So I multiplied by the angular acceleration alpha. Now next we will see some definitions or some important things, some definitions. So first of all we will go for kinetic energy. So kinetic energy, a particle of mass moving in a circle of radius r is having kinetic energy is equal to, we know for linear motion we have already studied, kinetic energy is equal to half mv square, where m is the mass and v is the tangential velocity. This is what we have studied in our linear motion. Kinetic energy is equal to half mv square. Now coming to rotational motion, kinetic energy is equal to half. So mass is replaced by moment of inertia. Tangential velocity is replaced by angular velocity, omega. See, tangential velocity is for curvilinear motion. Omega, angular velocity, is for rotational motion. So for linear motion, kinetic energy is equal to half mv square. M is mass, v is the linear velocity. For curvilinear motion, kinetic energy is equal to half mv square, where m is the mass and v is the tangential velocity. For rotational motion, kinetic energy is equal to half I omega square, where I is the mass moment of inertia and omega is the angular velocity. Now, see, we have studied in our third module, while we are studying this center of gravity, moment of inertia, mass moment of inertia, we have studied what is I. That is the relationship between K, radius of gyration. We have studied what is radius of gyration. So radius of gyration is equal to root of I by A, moment of, for area moment of inertia. So for mass moment of inertia, K is equal to root of I by M. Area is replaced by mass. So our radius of gyration K is equal to root of I by M. For this unit, we will discuss about masses, right? We are studying about kinetics. We equate the mass. So moment of inertia, relationship between moment of inertia and radius of gyration is I is equal to mass into k square. K is the radius of gyration. Okay, now we know work done is equal to force into displacement. For rotational motion, work done is equal to torque into displacement or moment into displacement. So T into, here it is angular displacement, so we take it as theta. And when we are integrating, integration of T into d theta, integration of every torque multiplied by the smaller angular displacement. So we know omega, that is angular velocity, is equal to differentiation of angular displacement, that is omega is equal to d theta by dt. So by substituting d theta is equal to omega into dt, we get work done is equal to integration of t omega dt. Just you remember, work done is equal to torque into displacement, force into displacement, or moment into angular displacement. Now, what is the power transmitted? Power transmitted due to the torque applied. So, power transmitted will be equal to the torque applied multiplied by the angular velocity. Now, angular momentum. So, angular momentum is equal to I into omega. We know linear momentum is equal to mv, mass into velocity. Here angular momentum is represented by h, that is equal to I omega, moment of inertia into angular velocity. Now angular impulse, we have already studied impulse is the force applied, a large force applied on a short duration of time. Now here angular impulse is equal to torque into T. We have already studied linear impulse is equal to force into time, short duration of time, Ft. Angular impulse is equal to T into T. T is torque into the time. Now we have already studied the work energy principle. So work energy principle is moment into theta or torque into angular displacement, m theta or t theta is equal to half into omega square minus omega naught square, that is final angular velocity. Omega is final angular velocity and omega naught is initial angular velocity. So work done is equal to change in kinetic energy. And impulse momentum principle, we know mt is impulse. So impulse momentum principle, momentum is I omega. So when we have initial velocity, initial angular velocity and final angular velocity, the impulse momentum principle is impulse is equal to change in momentum. That is impulse is mt is equal to I omega minus I omega naught, that is change in momentum. So I into omega minus omega naught. So angular impulse is equal to change in angular momentum, that is impulse momentum principle. Now just a comparison between the linear translation and rotational translation. So we know for linear translation, Newton's second law is force is equal to mass into acceleration. So for rotational motion, moment is equal to moment of inertia into angular acceleration. The work energy principle is, see, work done, work and energy. We are relating the work and energy. So work done is change in kinetic energy, that is work energy principle, relating work and energy. So work is equal to change in kinetic energy. So work done is force into distance, change in kinetic energy is half mv square. V is final velocity minus initial velocity, so v square minus u square. Here work is m theta, energy is half I into omega square minus omega naught square. Now impulse momentum principle, relating the impulse and the momentum. So impulse is equal to summation, so total impulse is equal to change in the momentum. So impulse is Ft for translation and impulse is mt for rotation. Now momentum is mv for translation and I omega for rotation. So impulse is equal to change in momentum. So what is Newton's second law? Work energy principle and impulse momentum principle. So work energy principle relating work and energy. So work is equal to change in kinetic energy. Impulse momentum principle is relating impulse and momentum. So impulse is equal to change in momentum. Now we will solve two problems today. So example 1. A flywheel of weight 25 kilonewton and having radius of gyration 0.5 meter loses its speed from 200 rpm to 140 rpm in 1 minute. Calculate the retardation torque acting on it. Change in kinetic energy during the above period and change in angular momentum during the same period. So three things we need to find. Retarding torque. So torque. Because see the speed is changing from 200 to 140 revolutions per minute. So the speed is reducing. So automatically we will have a retardation torque. That is a reduced torque. Then change in kinetic energy. That is half, kinetic energy is half I omega square. So half I into omega square minus omega naught square. And change in angular momentum. So just see, every data is given for you. Just substitute in the formula and find the answer. So we know weight is given. Weight of the flywheel is given as 25 kilonewton. So mass of the flywheel is 25 multiplied by 1000 divided by 9.81 kilogram. Now radius of gyration is given as 0.5 meter. We know radius of gyration is equal to root of I by m. So from this we get moment of inertia, mass moment of inertia I is equal to 637.105 kilogram per meter square. Sorry, kilogram meter square. Now initial angular velocity is given as 200 revolutions per minute. So we convert it into radians per second. We have to multiply it by 2 pi and divide it by 60. So we get 20.943 radians per second. Similarly, the final angular velocity is 14.66 radians per second. The time taken is given as 1 minute, so that is equal to 60 seconds. Now using the impulse momentum principle, we know mt is equal to, that is impulse is equal to change in momentum. Mt is equal to I into omega minus omega naught. So from this we get m. See, m is moment. Moment is nothing but torque. T is given as 60 seconds. I is already found out. We know the values of omega and omega naught. So substitute, we get the torque or moment m is equal to minus 66.7169 Newton meter. That is negative torque, because in order to reduce the rotation, reduce the speed, we are applying the torque in the opposite direction. That is the meaning of that. Now change in kinetic energy, we know half I into omega square minus omega naught square. So substituting the values, we get change in kinetic energy as minus 71.270. Now change in angular momentum, we know angular momentum is equal to, change angular momentum is momentum I into omega. So I into omega minus omega naught. It is 4003.5. That's all the first problem. See, everything is given, just to substitute. Now we will go for the second problem, last problem for today's class. A flywheel weighs 540 kilogram and has a radius of 2.4 meter, what constant moment must be applied to the wheel about its axis of rotation so that the angular velocity of the flywheel is equal to 30 revolutions per minute in 6 revolutions after the wheel starts from rest? So, initial angular velocity, see the flywheel weighs 540 kilograms. So, mass is given as 540 kilogram. The radius is given as 2.4 meter. What constant moment must be applied to the wheel about its axis of rotation so that angular velocity of the flywheel is equal to 30 revolutions per minute. So, that means initial velocity is taken as, initial velocity is not given. So, we assume that it is at rest. So, omega naught is equal to 0. So, final angular velocity is taken as 30 revolutions per minute. So, that is equal to pi radians per second. Now, angular displacement, we are asked to find the constant moment or torque applied in 6 revolutions. 6 revolutions. Revolutions means it is nothing but angular displacement. So, the angular displacement is given as 6 revolutions. So, that is 12 pi radians, converting revolutions to radians. Multiply it by 2 pi. So, we get 12 pi radians. Now, mass moment of inertia, see it is given as a flywheel. So, it has a radius of 2.4 meter. So, now we know, see we have already studied in our third module, the mass moment of inertia for a disc is mr square by 2. Mass moment of inertia for a disc is mr square by 2. For a circular ring is, mass moment of inertia for a circular ring is mr square. Mass moment of inertia for a circular disc is I is equal to mr square by 2. So, by substituting the values, we get mass moment of inertia for this flywheel as 1555.2 kilogram meters. Now, by substituting omega square is equal to omega naught square plus 2 alpha theta, that is v square is equal to u square plus 2 alpha 2as. V square is equal to u square plus 2as. So, you replace linear values by angular values. So, we get alpha is equal to 0.13089 radians per second square. Now, we know torque or moment is equal to I into alpha. So, substitute the values for I and alpha, we get 203.575 Newton meter. We have one more problem. Okay. So, problem 3, small problem. A belt wrapped around a pulley of 500 mm in diameter has a tension of 750 Newton on the tight side and a tension of 150 Newton on the slack side. Find the power transmitted if the pulley is rotating at a speed of 200 revolutions per minute. So, first of all, we will draw the diagram of the pulley. See, the diameter of the pulley is 500 meter. This diameter is 500 meter. So, both side, that is on the tight side and the slack side. See, one side you can take it as, since other conditions are not given for you, take one side as tight side and the one side as slack side. And both the side it is tension. See, both the sides of the pulley, tension, it is tension. One side it is a 750 Newton and the other side it is 150 Newton. Now, we know the formula for power transmitted is equal to torque into angular velocity. So, our aim is to find torque and velocity now. Now, angular velocity is given as 200 revolutions per minute. So, that is equal to, converting it into radians per second, we get 20.944 radians per second. So, net torque is equal to torque into radius. So, net torque is, we have two forces. So, force into distance, that is torque. or moment, force into distance. Here our forces are, we have two forces. So we have to take the net force. So net force is nothing but the net tension. So the tension is 750 minus 150. So multiplied by the distance. Distance is the radius here. So radius is 0.25. It is given the diameter as 500 mm. So 250 mm. So radius is equal to 0.25 meter. So we get 150 Newton meter. Now the power transmitted is equal to T into omega. So we get 3141.6 watts. So that is equal to 3.1416 kilowatts. So thank you. That's all for today. Hope you all understood. We will see some more problems in our next class. Thank you once again. Thank you.